I'm not nervous. I'm just not happy with my lack of results. So.
Our first speaker today is Desiree. Desiree received her BS in electrical engineering from Rensselaer Polytechnic Institute in May 2012 and her MS in electrical engineering from the University of Illinois at Urbana-Champaign in May 2014. She spent her past 2 summers at PowerWorld working on transient stability computational improvements. Desiree's research interests include data mining, power system simulation, and power system computational techniques. Under advisor Thomas Overby, her work currently focuses on algorithms for distribution level data analysis.
Thanks. Okay, so as Andy mentioned, my name is Desiree Phillips. So I'll just, oh, yeah. So the title of my work is Classification of Distribution System Events Detected by Frequency Disturbance Recorders. And so first off, I'll introduce frequency disturbance recorders, which are the PMUs that I use in my work. And then I'll go into how I analyze the data that comes into these FDRs. So I've presented before, so I'll kind of just mention some of the results that I showed from that work, and then some changes I've made to the data analysis, as well as introducing convolution for event detection. And then I'll suggest or list my conclusions and future work. So frequency disturbance recorders, those are the devices there. The device there, it's a voltage measurement device. It takes in only voltage data, no current data, at a rate of 10 hertz. So I get frequency, voltage frequency, magnitude, and phase at a rate of 10 hertz. So my research focuses on the FDRs that we actually have installed around Urbana-Champaign. We have had 7 in the area collecting data since December 2012, and so my work focuses on analyzing the data that comes from those devices. So just some limitations of the devices I use. They don't have any auxiliary power supply, so in the event of a blackout, I don't get that blackout data. There's no internal memory buffer, so if I lose the internet, I don't get that data. And so, and again, there's only one sampling frequency available. Some devices can do 30 or 60 hertz, and so there is some work being done with some groups on campus that are trying to create a voltage measurement device that addresses these issues while still being cost effective, but I won't go into that since that's not my area of focus. So the analysis techniques I've been using for now standard deviation just for event detection. There's a sudden increase in the standard deviation. That means there's a sudden increase or decrease in the voltage at that point in time, and so I use that as one way to detect events. I also use the Fourier transform for oscillation analysis, and then min-max for the change in voltage over an interval. The way I've been analyzing this data so far has been using the sliding window. So I'll have a sliding window of a given length of time. In my case, I've been using 10 seconds. And so for each 10 seconds of data, I record the standard deviation and some of the FFT parameters for that window. And then I evaluate that change in value over time, and I use that to see if there's any events going on within the power system. So before I can actually analyze that data, I do need to at least clean it up somewhat. And so the goals of my cleaning were to remove noise spikes within the data, as well as improve the accuracy of any algorithms I may use in the future. And so in a way, the data processing is dependent upon which algorithms I decide to use to analyze the data. So previously, I was actually using a median filter. So just for a given set of points, I'll take the median of that data and I'll use that to kind of clean the data over time. And for the FFT, just to get rid of the large DC component, I did a mean detrending, or I detrended by the mean. These two plots, this is just an example of the voltage magnitude and frequency over 1 hour of time, just so you can see kind of how the voltage at one location varies. You can see that in particular, there's a noise spike here and one here that my median filter was able to clean out. So this was using the median filter. These were the results I got. These are the standard deviation. And so my code actually went through and also marked off any of the peaks in the data, and I, sorry, and it's not, okay. And I just plotted some peaks just so you can see the kind of events that were going on within the data. So part of my research is actually identifying what some of these peaks may be, and I can kind of do that hopefully based on where they occur, how often in a day they occur, if there's anything going on at other devices when these events occurred. So some of these, this one appeared to be a tap change just because you can't see it here unfortunately, but before and after this event, the voltage remains relatively constant, which implies some sort of tap change. This bottom figure, this appeared to be some sort of generator or motor startup because it seemed to drop and then gradually level off in a manner that's similar to motor startup behavior. So it's kind of me, so I can kind of eyeball it right now, but the goal of my work is to have the code do this for me, and so it's kind of tricky in working with it. So one thing I wanted to change was the median filter. The median filter is nice in that it removed the noise spikes, but as you can kind of see in this data, the median filter, which is the red line, tends to cut out a lot of what may have been going on in the original data. And so in that sense, it was a little too powerful. So I wanted to try and use a different filter that wouldn't necessarily eliminate all those data points and straighten them out too much. So for now, I've actually switched to the Savitsky-Galais filter, which is a polynomial smoothing filter. So I can specify the order that I want to do it, like a third order filter, fifth order filter, and as well as what size window, much like the median filter, how many data points I want to use for that smoothing at each point in time. And so this was plotted out using the same specifications for the median and Savitsky. So for now, I'm using Savitsky, but if something else happens to come up, maybe I might switch to that. And then you can kind of see, this is just a plot. The top two are these events detected with the median filter on, and then those same events detected with the Savitsky-Galais filter. So you can kind of see those oscillations over here, which were all but eliminated in the median filter. But part of my work will actually look at improving the accuracy of the filter because it's a polynomial filter. It does have a habit of introducing oscillations where they may not have been if I don't specify the right parameters for the filter. So part of my work will be looking into that as well. But so the convolution. So the way I'm doing the convolution is if I have an input voltage signal, maybe the voltage over 1 hour, and I have one of these events, I've decided to call it event 1. And I want to say, okay, I don't know what event it is, but maybe I can use where that event occurs and how often it occurs as a measure of, or as a way to help identify what that event could be. So in convolution, if you have two signals, for example, this could be the input voltage data, and this could be the event that I'm looking at. If I were to convolve those two signals, basically what happens is at each point in time, you basically slide the figures together, you take the area shared by them at that point in time, and you mark that off as a point in your curve. And so as the area increases, so does the value on the figure. So hypothetically, if you have the waveform and you're sliding it across and it runs into an event that's exactly the same, the area will be maximal and you have a peak at that point in time. The issue is, right now, what will the peak of that event look like versus the peak of other events that I may pick up in the waveform? And so the work will be looking at properly isolating whichever peaks correspond to the event I want versus peaks that may correspond to other similar but actually completely different events. And so unfortunately, I don't have the code or results for that. I'm still working on that part because it gets a little tricky differentiating between the peaks, but part of my work will be looking into that. So just to kind of sum up what I've been doing and propose what I'll be doing or show I'll be doing in the future, Savitsky-Galais is a little bit better at filtering my data because it can still get rid of those noise peaks efficiently, but it doesn't exclude or doesn't completely eliminate the data in other points along the voltage data. The convolution could be used to detect the peaks, but the issue comes in with, again, as I mentioned, differentiating between peaks of interest versus peaks of other events. And so my work for now will be kind of looking into that convolution. And so, I'm sorry, that should say convolution. So my goal is to quantify and or qualify how I can differentiate between events with the convolution and basically look into that. And then if I can, maybe use additional FDRs and examine whether, if the event happens across multiple FDRs, maybe that tells me something about where it is or what it's doing or what's happening with the grid at that point in time. So this is kind of on the side, but for now I've been mostly using MATLAB for a lot of my code. So MATLAB's nice for the mathematical computations, but the primary disadvantages that I see are MATLAB's very memory heavy, and so the more code you work with, the slower MATLAB starts to get. And so in the future, since I'll be working with data sets that we are getting, I want to kind of work on all aspects of it, from data storage, storing that data, mining the data, data conversion. Since there are multiple PMU formats, IEEE has its own format. JSIS is another format. And so I kind of want to have the ability to convert between data formats if I need to. And so MATLAB could potentially do those things, but it may not be as computationally efficient as if I just wrote my own software to do so. So that's also what I've kind of been working on, was writing up my own software to handle all of those tasks. And so we'll see where that goes. So just to acknowledge, ISEG, Illinois Center for a Smarter Electric Grid, has been funding my work so far, so I'd like to give them a thank you for that. And then I can open the floor to any questions. Yep.
So I think that one part of this is about trying to identify what actually has occurred.
Yeah. Yeah.
Is there a way to do that without first characterizing types of events that can occur by measuring them when you know they have occurred, and then using some sort of a database that would compare what is occurring to what you know those types of things look like? And I feel like that's a huge part of data is actually doing that.
It is. So the way I'm working, so since I'm in a sense completely blind in that aspect, what I'm trying to do for now is just give each event a unique identifier. So maybe in the future I run a Power World case, or I get some data from another distribution system, and then I can say, I have 10 unique events that I've detected. I don't know what those 10 are, and then I can maybe compare those 10 to the distribution event that I'm getting in, and maybe at least in that sense I can start to get a better idea of what's going on in the grid. So in a sense, I'm actually completely blind, but in the future that would be part of what I'm doing.
Have you done anything where you introduce this distribution level event and measure what happened in order to get a picture that you recognize?
I want to. So since Amarin is around the area, and we do kind of talk to Amarin and work with them, I don't have any Amarin in contact of my own, but I do in the future want to have one that I could potentially introduce these kind of experiments. I could do that too, since Overby does have a device at his house, and he does have his own backup generator. So yes, but the problem is his signal is actually really noisy. Like if I plot out everybody else's signal and then I plot out Overby's signal, you can always tell which one's Overby's because his is so much noisier. I don't know. It's like this constant, I don't know, like it's not even white noise, it's like Overby noise. It's like this constant, I don't know what it is. So his data set is a little bit trickier to work with in that aspect. Yep.
Your power thing is kind of reminding me of something. So we went to the Leadership Computer on campus, and they said that in the fall they switch over from their own chillers to the campus chiller system, like where they get all their cold water from.
Mm-hmm.
And so that's a massive load for the university. You might want to contact them to see when they're going to switch over from their own chillers to campus chillers. That's a pretty large load. So it's something where it's not a big event, so it's a really large
Do they have any kind of data or something? Like,
No, so that's a huge load change, so the campus generators are gonna slow down. The 3.6, it's just an example. Anything.
no, I'm just wondering if we have a campus device is all I'm asking, because that would be. Right, but I don't know where that one went. I'm not in charge of. Oh, okay. I'm not in charge of it, but I would like to. No, I mean you could email me that data actually.
So I don't do measurements like this. I'm just saying.
Well,
I know.
no, I'm just saying you could email me that date so I can keep an eye out for
I
it.
don't know the date.
Oh well.
I'm saying you can talk to them and figure that out.
Okay, I will. Yeah. Sure.
Have you, like, is the 10 hertz sampling, is that quick enough to capture everything you would like to capture, or do you wish it was faster? Or?
I wish it was faster only because going into this project, Overview was kind of like, or me and Overview were kind of like, let's see what we can see. So in that sense, maybe there's not a lot to see at 10 hertz, or maybe there's not a lot of unique events at 10 hertz. A lot of PMUs can go up to 30 and 60 hertz, and so you always kind of wonder what kind of events, because you can probably see the faster like generator oscillations. You can see it at those frequencies, but I can't see it at 10 hertz. So there are some events I would like to see. It'd be kind of cool to see, but for now, I guess I'll be content with the events I managed to pick up.
And then also, did you ever put like a UPS on one of the units, the uninterruptible power supply, so you could actually, if it does power go out, you actually do still have it?
Overbee actually did that in the very beginning when we first actually got the devices, and it actually interfered with the measurements of the. Yeah.
We were going to modify the units to do that. I don't know if it ever got done. It was kind of started.
Yeah.
Like the problem with why we can't do it easily is because it doesn't have one plug that's for power, one plug for sensing. Like it's just the same plug that you plug into the wall, and so that's the other part of that is like why it's like yeah. So there isn't any good easy way to like power it from the UPS because then your sensing would just
Yeah. Cool. Thanks.
Yep. Oh. Rock, paper, scissors. Okay, great. Yeah. Yep.
First of all, I'm sure that people that worked on the updated versions of this, like in our
Like Kenta and them. Yeah.
would probably appreciate if you like comment with like feedback into exactly what you want, if you haven't already. But the other thing I was wondering was, so you're basically talking about event detection,
Mhm.
and I don't know the professor, but I know there's been significant work done on load detection, basically load identification.
Okay.
More like a resonance level, so basically detecting the signature of different types of loads.
Okay.
And so I didn't know if maybe maybe some of that research might be helpful in terms of data mining or data sensing or.
It probably could in the sense that it could be used as training data in a sense, or at least events that I can use for comparison's sake. So definitely wouldn't hurt. I'll look that up if you can. Yep. I say yes, but it depends on where they are. So I actually mapped out the ones we have right now, and 3 of them are actually so close that, in a way, it's nice that they're close since the voltage is fairly local. I can kind of see the relative voltages at each location, but it's also pretty bad in the sense that they'll always be fairly similar, and so it depends on whether there's sort of a trade-off, and then there's sort of what kind of information would best help me identify the events right now. And so I wouldn't say no, of course, but it depends. I'm not sure where I would want to put them if I did. Yep.
So I thought I saw on slide 2 or 3 that the device samples at 14 to 40 seconds. Is that correct?
Yeah.
So what does it do with the data, the window averaging inside there?
They have a low pass filter, so they do some internal calculations using an IC and a low pass filter to get rid of some of that initial noise that comes in.
So what's like the peak frequency resolution you can see?
Peak frequency resolution. Well, it's 10 hertz data.
So if the sample's at 1440, then you can see what 700 or so hertz measurement.
No.
Like you can resolve 2 times. You can resolve 1/2 of your sampling frequency. Right?
No, so the thing is, it's samples at 14. So I work on it. So it's samples at 1440, but sampling like the side table is giving you at 10 hertz is the user, and so it has to do with like frequency, right? So when you do that, you will do it. So that's how it goes. It's not like it.
No. Yeah, I understand, but like so if you sample at 1440, then your highest frequency resolution has to be what 700.
It's not half of that.
Yeah. I know. So then like let's say that there is a signal that's like 500 hertz, and then if you are getting rid of or low pass filtering, then you can't even use that 500 hertz signal. So I was wondering like what is the highest frequency that you can output in this device? Because it's not 60 or 65. It has to be something less than 700.
I'm not sure because every time Overview's trying to ask for kind of the internals of the device so he can do those kinds of things, they don't want to share it.
Because it's some company or
It's not even a company. Okay. Any other? Yep. Um, they are in certain points, and so I can kind of see where the common events occur because the correlation suddenly jumps in value. So I can see that relationship, but more often than not, they're just so different that it's more often than not, they're really not that correlated at all. Frequency propagation in yeah. Yeah, that is one thing. It's weird. I tend to jump back and forth between voltage and frequency a lot, but I've started focusing on frequency recently just because frequency is such a global parameter, and or at least in the distribution system sense. So it's easier to correlate when a frequency event is detected versus when a voltage event is detected. But I haven't looked into that, but that was one thing I did want to do. Any other questions? If not, thanks. You volunteered me. How dare you? You volunteered me. So mean. You just put it like
Here?
oh
If you just right click.
oh yeah.
No, not the Java.
Maybe so slow. So, at least Professor Owen is not here today.
I know, right?
Yes.
Is that yours?
Oh, yes, that's mine. Thank you.
I had some old ones on my way. So you can stand over there.
Oh, I don't know. How do I know?
Oh, now it is. Check, check.
Oh, I don't know. Hello?
Well, our second speaker is Uyen. Uh, okay, our second speaker is Uyen. Uyen is a um, second year master's student under Professor Overby. She's from Vietnam and completed her undergrad at Ho Chi Minh University of Technology, Vietnam. She also had a 1-year exchange at UIUC during her undergrad, and her research is about GICs and their sensitivity to substation grounding resistance. So, thank you.
Hi, everyone. I'm Uyen, and today I'm going to talk about what I've been doing for more than a year. It's about GIC and its sensitivity to substation grounding resistance. So 1 year ago, I also made a presentation in the power seminar about this topic, but at that time, my algorithm only worked for local substation grounding resistance. This time, I developed my algorithm to make it not only can calculate the sensitivity to the local resistance, but also for the external resistance. So let me introduce something about GIC and why we have GIC in the power system. So geomagnetic disturbance is the phenomenon caused by a solar storm, and it induces a quasi-DC current flow in the power system. This almost DC current can cause half cycle saturation to transformer, and it results in the harmonic currents and the loss of reactive power demand. And I focus more on GIC at the substation because this GIC flow directly to the transformer, hence it causes the most damage. The GIC can be calculated based on the topology of the system, the resistance of transmission line, transformer, and the resistance of the substation grounding. Although the other resistance, like resistance of transformer and transmission line, usually include in the power flow model, but the substation grounding resistance are not readily available, and the value that used to study usually just estimated value, and that can cause the that can make our calculated GIC unprecise, and that's why I study the sensitivity of the GIC to the substation grounding resistance. So first, the GIC can be calculated, can be solved by first obtaining the voltage of all the nodes in the system using the equation V equal to G to the power minus 1I, with V is V contains the substation neutral DC voltage, and I contain all the injected current. To calculate the injected current, we take the induced voltage along the line and divide by the resistance of the line. And the injected current is the sum of all the current flow into the line, or flow into the node, sorry. G is constructed similarly to the admittance matrix, but because here we only deal with the almost DC current, the quasi DC current. So G matrix only contain the conductance value and like resistance. And transmission line with series capacitor are omitted. Transformer are modeled with their winding resistance. So my sensitivity is defined as the percentage of the difference of the GIC and the difference of the grounding resistance. And to the equation below show the way I calculate the GIC at node I. And sorry. So in the equation, we can see that the GIC depends on the vector V, and according to the first equation I show, V is equal to G to the power minus 1 I. So we can see that the GIC depend, to calculate GIC, we need the knowledge of the G matrix. And because G matrix contain the substation grounding resistance, so it also not precisely known. So I call I prime, IGIC prime is the GIC with the because the substation resistance is not a known value, so it's just usually only estimated value. And I call the I prime as the the real value that we don't know, and the I1 is the estimated value that we use. And in here we see that in the equation of the GIC prime, it has the matrix G prime, which is the G matrix with the exact value of the grounding resistance, which we don't know about that. And we have the GI is the difference between the estimated value that we use and the real value. And in here to calculate the G prime, in the inverse of G prime, we need to use matrix inversion lemma. And also because G matrix is sparse, so to find the invert of it, I use the sparse matrix vector method, which allow us to find the elements of the inverse matrix without like doing the inversion for the whole big matrix. And this is my equation for the sensitivity at the local resistance. In here, I show it in two forms. The first form show it depends on show that the sensitivity depends on the GI, which is the admittance of the of grounding of the grounding, and RII, which is the element of the resistor matrix, which is the inversion of the conductance matrix G. So RII is obtained by using sparse vector method on G. And the second form of it is the last equation, show that the sensitivity at the local resistance is always the negative number, mean that if the real resistance is higher than the estimated resistance that we use, then the GIC, the real GIC is smaller than the GIC that we calculated. And this one is the sensitivity to the external grounding resistance. And this one also depends on GI and element Rij, which is the element of the G matrix, of the inversion of G matrix, and the value of voltage at node I and at substation I and substation J. So I apply my algorithm on the 20-bus system, and in this system, substation 1 is blocked, and substation 7 has no ground to pass, so they are omitted in the matrix. And this is my result. So the sensitivity here show, the value of sensitivity here show that for 1 ohm change of the resistance, then it according to for 0.01 ohm change of the resistance, it leads to this value percent of change of the GIC. Like as an example, let's look at the value, the sensitivity of GIC 4 to R4. The value is minus 0.802, which means that if the difference between the estimated value and the real value is 0.01 ohm, then the difference between the calculated GIC and the real GIC is about 0.8%. And the value 0.01 ohm is actually small. The difference can be the normal difference can be 0.1 or even 0.5. So you can see that, let's say if the difference of the resistance is 0.5, then the difference of GIC is almost about 40%, which is big, and which means that the GIC that we got is totally different from the real GIC. Now I apply it to the larger system, and I use an equivalent system, about 10,000 bus, and this system is equivalent to an EI Eastern Interconnect system, which about 62,000 bus. And in this system, only a small number of substation grounding resistance are known, and other are modeled with just a simplistic model. And from this, from running the algorithm on this system, I found that I looked at the 10 substations that have highest GIC, and I saw that the sensitivity to the local resistance are much higher than the sensitivity to the external resistance. And also for only the neighboring substation grounding resistance have trivial impact. So I choose the one with the resistance is higher than 0.1, which means that if the difference between resistance is 0.1 ohm, then the difference between the GIC is 10%. So I choose it as the threshold, and I found that only substation at around 5 hop, mean like it takes them 5 hop to reach each other, have satisfied the threshold, the sensitive threshold. Thank you. Do you have any questions? Yes.
Can you go back to 3 slides where you had a big table?
Oh, this one?
So is there a reason why substation 3 and 5 and 6 have really high sensitivity to their own resistance, while 1 and 2 and 4 are really low?
So the sensitivity here is also the let me think just how to say it. So I mean like it.
You know how the values of internal resistance change between the different substations, like where some really high and some really low?
Yes, yes. So that's what I mean. So the substation, a substation like a substation 3 with the resistance 0.2. So we can see I can see that the sensitivity is high, but let's say so. Um, Let me compare between substation 3 and substation 4. So substation 3 has the resistance 0.2 and substation 4 had resistance 1, and all of them just estimated value. But like, but I mean that the difference between the uncertainty of substation 3, it it may be lower than substation 4, right? Because like substation 4, the estimated value is 1, but the real value can be like 1.5 or like 0.6, 0.7 something. But with substation 3, the difference between the real value and the estimated value may be smaller. So it may be the estimated value is 0.2, so the real value can be maybe 0.3 or 0.1, something like that, right? So the difference of the at substation 4 higher than the difference at substation 3. I'm sorry. So apply it to the sensitivity, and the sensitivity is mean that according to 0.01 ohm, it leads to the difference of this value percentage of GIC, right? So let's say in substation 3 with the value -2 here, I got the difference resistance is 0.1. Then the change of GIC is about 20%, right? But for substation 4 with the value of 0.8, but the difference can be like 0.5 ohm. So the difference, the change of GIC can be 40%, right? So that also depends on the value and about the uncertainty of the resistance of the value of resistance that we know.
So one of your conclusions was that like the GIC doesn't travel very far in the network, more localized.
Yes.
So it finds a way out of the system within the first few buses or something.
Yes.
So like once this sensitivity analysis gets applied to like optimal blocking strategies and things, what do you think the GIC in the network is going to do? So it's going to redistribute, and then I would think that it wouldn't be like as local anymore, because if you have two different networks and one person's blocking all the GIC in their network, it's still going to have to flow in and flow out of somewhere. So where do you see, like, how do you see this research fitting into that? And how do you see like the results changing, if any?
I'm sorry about this question. I'm not sure because I didn't do anything with the blocking device. So right now I cannot imagine like if we have a blocking device and how the change of GIC.
Do you plan on extending this to like blocking algorithms or anything like that?
Yeah.
Yeah. Okay. Cool.
Thank you.